Okay, plate tectonics. The first thing to understand in plate tectonics is we need to understand seismic waves, because that is where we really understand what's on the inside of the Earth and what drives plate tectonics. So there's actually three ways that we've learned about what the inside of the Earth is made of. So how do we know what the inside of the Earth is made of? Well, there's seismic wave information, which is whenever we gather information about how waves travel through the Earth, where can they travel to, where can't they travel to. The other thing is that we've realized that Earth's density, its overall density, is higher than the density of just the crustal rocks. So if the density of the whole Earth is greater than what it would be if it was just crustal rocks, then we know that whatever is in the center of the Earth has to have more mass than what is at the surface. The other thing is that we know what meteorites are made of, and meteorites were part of the early solar system. Meteorites are made from the materials that formed in the early solar system, and so they give us clues about the composition and the proportion of the different substances that make up the Earth. So what are seismic waves? Seismic waves are basically just waves that travel through the Earth's layers, and they can be caused by earthquakes, volcanic eruptions, magma movement, a large landslide, or even a man-made explosion can let out this low energy or low frequency wave of acoustic energy. Like I said, seismic waves are basically just sound waves that are traveling through Earth's rocks. So how do we detect those? Well, scientists all over the world have these devices known as seismographs. And what they are is a pen that is attached to a heavy mass that is loosely suspended. And so when the Earth shakes, the inertia of the pen keeps it in position, but the Earth and the whole device shake around it. So you'll notice in the animation that the pen and the weight are not moving, but that the Earth and the whole rest of the apparatus, including the paper, is what's moving, and that is what generates the line on the seismograph. On the bottom left of the screen, you see an actual picture of a seismograph. And in the top right-hand portion of the screen, you can notice how the P waves create much larger amplitude waves and have much more damage on houses and stuff than the P waves actually do. So how are P waves and S waves distributed? Well, P waves and S waves actually propagate through rock differently. P waves travel like a pulse. They're known as primary waves because they are the first to arrive. And P waves are capable of traveling through both solids and liquids. So look up at the P wave and you'll notice it kind of looks like a pulse through a slinky. Down at the bottom, S waves, known as secondary waves because they arrive later and are known as the aftershock, and like I said, they're more destructive. You can think of S wave as the snake-shaped wave because snakes squiggle that way, and they have even the shape of the S looks the way that an S wave looks. And the most important thing to remember about S waves is they can only travel through solids, right? So even more S alliteration there. So S, secondary, snake, solids, okay? That's the only thing they can travel through is solids. So what does that tell us? Well, if there was an earthquake at the North Pole, all of our presents would get destroyed, but also there would be no S waves detected anywhere below 103 degrees latitude, south latitude. So in the right-hand diagram, you'll notice that there are no S waves detected if there was an earthquake at the North Pole. However, P waves are able to travel through the Earth's core because P waves can travel through a liquid, but S waves cannot. And so because of these shadow zones, these shadow regions that are created where seismic waves can be picked up, because of the shadow regions, that's how we know that the outer core of the Earth is liquid. All right, so what can we learn about the inside of the Earth from the difference between where P waves and S waves can be detected after an earthquake? We can learn that the outer core is liquid. All right, so the layers of the Earth then. Well, we can basically break up Earth into four main layers. We can talk about the crust and the lithosphere together because they behave the same way. They are brittle and they are the least dense, which is why they're at the Earth's surface. The mantle, a little bit deeper, has a property known as plasticity, and the asthenosphere is that uppermost liquidish layer of the mantle. Next layer deep is the outer core, which has swirling liquid iron and nickel, and it is what creates Earth's magnetic field. And the inner core is solid. The lithosphere. The lithosphere is what Earth's tectonic plates are made of, so sometimes you'll hear them referred to as lithospheric plates. And the lithosphere is mostly composed of the least dense elements. Now, we have some heavy elements, but not nearly as much as there would be in the core. So the most abundant is oxygen, then next comes silicon, aluminum, calcium, iron, sodium, potassium, and magnesium. So silicon and oxygen make up the most of the crust. And that's what soil is made of, it's what granite is made of, it's what all of these rocks are made of. And the lithosphere is cold because it's at the surface, and it's very brittle relative to the deeper layers. It's the one that was represented by the Oreos in our treat that we made. The tectonic plates basically float on the mantle below. Okay, now the mantle, Earth's mantle has more mass and volume than any other layer of the Earth. So basically the majority of the mass and volume of the Earth are the mantle. So the Earth is mostly mantle. The mantle is composed of oxygen and silicon in the form of silicon dioxide, and convection currents, that lava lamp effect, is what takes place in the mantle. And so there you can see the mantle, the convection currents, and whenever the mantle gets hot at the bottom, it starts to expand, becoming less dense, going up to towards the surface of the Earth. Where it cools off, becomes denser, and then sinks back down. And so it creates this cycle of a current, and it's just flowing and churning, okay? And it has the ability to do this because the mantle is plastic, meaning that it has the ability to flow. The same way, whereas you added heat, you were able to kind of mush that Tootsie Roll around when you were making your treat the other day. The asthenosphere, represented by the frosting in our lab, is the liquidy upper portion of the mantle, and it drags the lithosphere along like a conveyor belt. So it is what is pulling those tectonic plates along. All right, so here is convection in our mantle, and it is basically the cause of the tectonic plate movement. In the center of the diagram, you can see some seafloor spreading, and at the edges, outer boundaries, you can see some subduction happening. All right, the outer core. The outer core is it's swirling, and it's a swirling liquid made of iron and nickel, and it's what creates Earth's magnetic field. Okay, so the outer core is made of iron and nickel. Its temperature is between 2,000 closer to the surface and at about 5,000 degrees Celsius closer to the inner core. It contains radioactive elements, and when they break down, they produce heat. And the outer core is liquid, whereas the inner core is solid, and this is because the outer core is less deep and therefore is under less pressure than the inner core. So even though the outer core and inner core are made of the same thing, the outer core is liquid because there's less pressure holding those particles together. Okay, and the inner core actually spins faster than the Earth rotates, which is an interesting fact about the inner core. It is also mostly made of iron and nickel. Its temperature is over 5,000 degrees Celsius. It also contains the radioactive elements that break down and produce heat. And although it's hotter than the outer core, the inner core is solid because it's under more pressure than the outer core, because it's deeper. Okay, so the deeper you go, the higher the pressure is in the Earth. Okay, and when you get, even though the outer core and inner core are both made of the same thing, because one is deeper and under more pressure, the inner core is solid and the outer core is liquid. All right, here's just another diagram that I thought was good. You can see the mantle, and that uppermost portion of the mantle is the asthenosphere, which is liquid, and it's dragging the brittle lithosphere along, and then you have the outer core and the inner core shown where they are located. So seafloor spreading, what's that? So seafloor spreading is caused by that convection current in the mantle, and when hot magma pushes its way up through the oceanic crust, it meets the water, cools off, and freezes into solid rock. This is the phenomenon that takes place at what are known as mid-oceanic ridges. So we see mid-oceanic ridges forming right here. This is the underwater mountain range that was discovered by Bruce Heesen and Mary Tharp. Now, where do we get evidence for seafloor spreading? Well, first we have magnetic reversal stripes. So the Earth's magnetic field hasn't always faced the same direction. North used to be south and south used to be north, and before that it was the way it is now, okay? The magnetic field of the Earth flips about every 500 million years, and they occur when the direction that the outer core is swirling changes direction. So if you look at the top diagram, you can see how the magnetic field of the Earth is nice, and like north is north and south is south, and then as a reversal is happening, there's a change in the swirling, and then what would eventually happen is that south would be at the North Pole, and north polarity would be at the South Pole. If you look down at the animation below, you can see that as that magma is freezing, depending on what direction the polarity of Earth's magnetic field is, the compass is changing direction. And so the dark lines represent when Earth's magnetic field was the way it is now, when it was the way it is currently, and then the white lines represent when Earth's magnetic field was reversed. And so we can see that throughout time, Earth's magnetic field has changed, and so the magma that is freezing at the center is the newest oceanic crust, and then as you get further and further away from the middle, you're looking at older and older and older oceanic crust. The other evidence was sonar data. Sonar data was collected during World War II, and it was compiled by Mary Tharp and Bruce Heason to build a topographic map of the seafloor. This was the first map that showed scientists the seafloor had this large, long, underwater volcanic mountain range. So those dark lines that you see on there are those mid-oceanic ridges. All right, so tectonic plate boundaries. The first type of boundaries are divergent boundaries. And so at the top, you can see a rift valley. This is known as continental rifting. So underneath a continent, if there's a hot spot underneath a continent, it'll start to split a continent apart. This is what split Pangaea apart. And then as you go down, you can see that it's starting to form an ocean floor beneath where there used to be, the continents used to be one. And then as you go further on, now you have seafloor spreading taking place. So divergent boundaries are always basically plates separating from each other, but oftentimes they start as rift valleys and develop into seafloor spreading. So here, seafloor spreading is the oceanic, when two oceanic crusts are separating. And then on the right-hand side, you can see where continental rifting is taking place. The Arabian Peninsula used to be connected to Africa, but there's continental rifting happening beneath it, and the Red Sea is forming there. All right, the other type of plate boundary is convergent boundaries. That's to converge means to come together. So depending on the types of plates that you have bumping into one another, you're going to have different things happen. So on the far left, you see oceanic continental. So if you have an oceanic plate meeting with a continental plate, what you're going to end up with is volcanoes, because the oceanic plate is going to subduct beneath the continental plate. It's going to melt, and that molten lava is going to rise up and push through the continental crust and form a volcano. In the middle, oceanic, if you have two oceanic plates colliding with one another, the same thing is going to happen as with oceanic continental, only the volcano will form right in the middle of the ocean, and you'll get what is known as an island arc. And lastly, on the far right, when two continental plates collide, they have a harder time subducting because both of them are not very dense. And so when they collide with one another, mountains get pushed up and you get a very high plateau. Okay, so this is the first type of convergent plate boundary, one in which oceanic and continental plates collide with one another. Oceanic crust is denser than continental crust, and so it is going to go below the continental crust as they're being forced together. And as it goes deeper, it gets hotter, and so it starts to melt, and that magma can rise up through the continental crust and erupt out of the mountain range there and create a volcanic mountain range. And so one of the good examples of this is along the South American west coast. we have multiple volcanic ranges. And so you can see all of those different bars of orange on that picture to the right. There are volcanic ranges which contain mountains that are active volcanoes. And so the Pacific plate is colliding with the South American plate, and the Pacific plate is oceanic, so it's subducting beneath the South American continent. All right, so here's an animation. You'll notice in the middle we have seafloor spreading, so a divergent boundary on the left-hand side of this animation, but on the right-hand side is exactly the oceanic crust subducting beneath continental crust, melting as it gets deeper, and then the magma rising up and erupting out as a volcano. All right. Another type of convergent plate boundary is when two continents collide with one another, two continental plates. Excellent example would be the Tibetan Plateau, or where the Himalayas and Mount Everest are. India used to be a separate continent, but then crashed into the Eurasian plate, joining those two plates together. And as a result, the two continental crusts, when they hit, they don't subduct very well, and what you end up with is them pushing together, kind of crashing together, and building up some mountain ranges. So the Himalayas are an excellent example of that. And lastly, you can have a convergent boundary in which two oceanic plates meet. And so you can see that when oceanic crust subducts beneath another oceanic plate, you get volcanoes, just like the other case of subduction. But when it rises up and erupts, it's erupting on the ocean floor. And if it erupts long enough, you can end up with an island. And so that volcanic island arc can start to form. And so if you look over to the right, you see Alaska. And off of the coast of Alaska, you have that tail. And that tail is known as the Aleutian Islands. And those are volcanic islands that happen because the Pacific plate and the Arctic plate there, or the Siberian plate, are colliding with one another. And the Pacific plate is subducting beneath the Arctic plate and melting and erupting and creating that chain of islands known as the Aleutian Islands off the coast of Alaska. All right, and the last type of boundary is known as a transform boundary. This is not converging nor diverging, and so crust is not being made or melted. The plates are just sliding past one another. This is also known as a conservative margin because no crust is being made or melted, or also known as plate junctions. So right in the middle of this picture where it says transform, where one plate is going the opposite direction of the other plate and they're sliding past each other, that spot right where it says transform is the transform boundary. All right, and lastly, this is not a boundary at all, but it is something caused by hot spots in the mantle. And so if you can have a magma plume right in the middle of a plate, and if you have a big convection current right under a plate in a hot spot, you can have a volcanic island that just comes out of nowhere. What's known as a shield volcano, which is the type of volcano that formed the Hawaiian Islands. And that hot spot has been in the same spot for millions of years, but the Pacific plate has kind of moved around. So as the Pacific plate moves around and the volcano is erupting, you're getting this island chain where the ones that are older are more eroded, and then Hawaii, the big island, is a newer volcano that is closer to the hot spot and is the most active and still erupting. And so you have things like the Hawaiian Islands. If you have a hot spot underneath a continent, you end up with things like Yellowstone National Park, where you have a very volcanically active region, and it's very, very hot under there, and you end up with things like geysers and things of that sort. Hot spots, an interplate hot spot, is what caused Pangea to break apart, and it can cause continental rifting. So like that earlier example of the Red Sea. And we were talking about divergent plate boundaries. So interplate activity can become a divergent plate boundary if it's there long enough. All right, so this very last picture is a diagram that shows all of the plate boundaries all in one picture. And so you can see you can see that there is a subduction oceanic right there. You have continental oceanic right here. You have continental rifting, divergent, moving apart. And then you have seafloor spreading right here, which is also divergent. So you have just about every single type of boundary except for continental convergence here. And then right here we have little transform boundaries between different pieces that are seafloor spreading. Here we have a hot spot right in the middle, some of that intraplate activity. So you can kind of study this diagram, take a look at it. It shows how everything is working. We see subducting happening here and here. We see that it's moving away from the seafloor spreading. We see that things are floating on the asthenosphere and that they're lithospheric plates. And so this diagram really has a whole lot of stuff in it. So go ahead and take a look at this diagram, pause it before I made a bunch of marks all over it, and you'll be able to use it as a resource for yourself. All right, thank you for your attention.